Okay, in this video, we're going to talk about what causes splitting. Okay, so let's have a look at let's take a look at this compound here. Okay, and we are thinking about the red proton and the spectrum that that's going to make. Now, on the carbon next door to that one, we can see we've got one proton on the carbon next door. So we know that n+1 rule, the signal for that is going to be split into a doublet. Let's see what causes that. Well, what causes it is, if we have a think about this proton. I said in an earlier video, I said that each proton behaves as a tiny magnet, okay, tiny bar magnet. Right, so HA, if the little tiny bar magnet, if it's got, say, upspin, right, the magnet is going to be like that. Right, now that is going to add on to the external field. It's going to, the external field, or the field experienced by this proton, is going to be a little bit stronger than the external field. It's going to have that much added onto it. Yeah. Okay, now you can imagine if HA had the opposite spin to that. So if it had downspin, well, what would happen then is the downspin, the magnet would be the other way round. We'd have south at the top there and north there. So that would be in the opposite direction to the external field. So that would make the external field a tiny little bit weaker. Now, if you've got, you've got a test tube with all your sample in it. Here's your test tube. Yeah. And you're going to have billions of molecules of your sample in there. And on average, about half of them, HA, is going to have upspin, and half of them, HA, is going to have downspin. So half of the molecules are going to have a field a little bit stronger, have the external field a little bit stronger, and half of them is going to be a little bit weaker. Okay, so let's just fill this in as a chart here then. So right, let's say the two spin states of HA, it can be up or it can be down. What's that going to do to the effect on the magnetic field? When this lot here is going to make it a little bit bigger, +1 unit, arbitrary unit, and this one is going to make it a little bit weaker, -1. So that means you've got 50% of the protons different magnetic field than the other 50%. So you're going to get a doublet. So here's your spectrum. There's going to be ppm down there, and you're going to get a doublet. Right. This one, the field is a little bit stronger, so, and this one, the field is a little bit weaker, so it's going to take, you're going to have the external field is going to be a little bit stronger to make it resonate. And you notice there that the peaks are the same height as each other, because it's a 50-50 chance of it being one way or the other. And we know when we see a doublet, that's what doublets always look like, don't they? They always have two peaks of the same height. Okay, so let's see what happens then if you have got, that was with one proton on the carbon next door. Let's see if you've got two. See what happens then. So I've got this chart ready here, ready to go. So same thing again. We've got this molecule here, but except this time we're looking at the red proton. We're interested in this one. And on the carbon next door, we have got two other protons, HA and HB. Right, of course, they can, each one, HA can be upspin or downspin. So let's have a think what happens first of all. We could have two both in the upspin, both upspin. We could have one up and one down, so that could be two possibilities, HA up there and HB down, or it could be the way around. Or finally, the fourth one, the combination you could have is both in the down position. So let's see what that's going to do to the field, so that's going to make the field a bit stronger by +2. That one will make it a bit stronger, and that one will make it a bit weaker. So the overall effect of that, of course, is going to be just no effect on the field. Same again for this one. They sort of cancel each other out. Both in a downspin, that's going to both be weaker, so that's -2. So if we draw a little, what's that going to look like then? So here is our ppm scale, and we know that if you've got 2 hydrogens next to you're going to get a triplet, aren't you? Well, let's look at this. Let's do this one first. That one is going to give you the one in the middle, and that's going to be not affected. Okay, but that's going to be twice as high as this one and this one, because there's 2 different ways that can occur. This one here is the field is going to be stronger, so you're going to get, that's going to be half as big. And this one here, that's going to be there, and that's going to be half as big as the central one. And there is our triplet. And if you look at all the you should be, aware that triplets always look like that, don't they? The middle one is always twice as high as the other 2, either side of it. Right, let's expand that now to make it what happens when you've got 3 hydrogens. So I'm going to just rub out this table and change it a bit. Okay, so first of all, let's get rid of that and put HC there. So now we've got 3 protons on the carbon next door. Right, so we've got HC here now as well. So rub all these out. And this is, let's say, the effect on the field. Okay, so right now we could have all 3. We could have 3 in the up position. So let's do that. And the next thing is we could have 2 up and 1 down. Now, there's a few different combinations of that. So 2 up, 1 down, or you could have it like that. Or the final way you could have that is like that. Okay, so that's that lot done. What's the other possibility then? We could have, we'll run out of space here as well, I think. We could have one up and 2 down. So we can have 1 up, 2 down. I have this one up and the other 2 down. Yeah. Okay. That's those 3 possibilities. And then the final thing is you could have all 3 in the down position, couldn't we? Just about got enough room there. Right, let's see what that does to the field. Right, this one is going to make it 3 times bigger, isn't it? Plus 3 units bigger, not 3 times bigger, 3 units bigger. This one, well, you're going to have 2 up and 1 down, so that's going to make it 1 bigger. This one is going to be 1 smaller, because you've got 2 going down, 1 going up. And this one is going to be 3 units smaller. Right, what can we say about the height of the peaks? Right, this one is going to be 3 times as big, and this one's going to be 3 times as big as that one and that one. So if we look at the spectrum, here's our ppm scale here. we're going to have these two middle ones. All right, so those two middle ones are going to be 3 times as high as the ones either side of it. Okay, so that one is that small peak there. This one is going to be that one. That one is going to be this tall one. And finally, that's going to be the little one down there. And that is our quartet. And if we look at quartets in the spectrum, they always look a bit like that. The two middle ones, 3 times as high as the ones at the side. Okay, so I'm sure you can appreciate we could go on and we could do it for 4, 5, 6, but we're not going to do that. As it all gets, I mean, this is beginning to get a little bit complicated here, isn't it? Doing it that. I was losing track of which ones are going up, which ones are going down. But there is a sort of a quicker way of, you've probably heard of Pascal's triangle in maths. Okay, Pascal's triangle is, so you've got, now that one here, that's 2. Because you add those, that number 1 and that number 1 together, don't you? That's going to be 1 there. For this one here, it's 1 plus 2 makes 3. Same there. This one, 1 plus 3 makes 4. 3 plus 3 makes 6. 3 plus 1 makes 4. And you can carry on like that. 5, 10, 5. Sorry, it's 10, isn't it? That's 5. And that's 1. Okay, so you can see now this, how it works is this, right? This is if you get a singlet. So you just have 1 big peak. This one is if you, this line is if you have a doublet. So you have the 2 the same height as each other. This line here is if you've got a triplet. So a triplet, you're going to go, that one's going to be 2, twice as big as the one either side of it, 1 either side. The quartet is going to be the 2 in the middle are going to be 3 times as high as the one either side. And then you get this one here is obviously going to be the quintet. And this is going to be the sextet. But these peaks, they always have kind of a symmetrical appearance like that, don't they? That sort of thing, which we are accustomed to. Okay, so that's what causes splitting in 1H NMR. I don't think they've ever asked what causes it, but you just have to know the rules, the n+1 rule. So this video, they've never asked questions on anything in this video, but it's just for your background information. And as we know, splitting is an extremely powerful way of working out the structure of a molecule from its NMR spectrum. Okay, so we'll leave that there.